Hello, with exercise 10a, we're going to look at differentiating inverse functions, which is quite similar to what some of the stuff we've done recently on using. I know we found times when we found, for instance, dx by dt, but we needed dt by dx and things like this. So that's what we're going to be looking at in this lesson. Okay, so reciprocals, let's just remind us, obviously the reciprocal of dy by dx is dx by dy. This is what we've been doing, been playing around with, perhaps finding this but then using this. So this basically just another way of saying it. If I find the reciprocal of dy by dx, I get dx by dy. If I find the reciprocal of dx by dy, I get dy by dx. So we can use the fact that they're reciprocals when finding these, and we tend to need to do this if ever we are given an equation which says x equals rather than y equals, because it's dead easy for us to find dx by dy because it's written as x equals. You can find dx by dy using y as your variable, so just treat it as like normal. 5 comes to the front, that's 20. Lose the power, so 20y to the 4. I suppose I should try my best to write this better. This is 8y. I reckon that's to the 1. I reckon that's to the half. So this is like to the 3 over 2. So minus, I've got to times the 3 over 2 by the 8, which I think is 12y to the half. And of course you could write that as 20y to the 4 minus 12 root y. Now that, remember, is dx by dy. The question says find dy by dx. So all I do is I flip it upside down. Depending on which answer I've come up with, it's 1 over 20y to the 4 minus 12 root y. And that's exactly how I've written it, as it turned out. So relatively straightforward to go from an equation for x equals to dx by dy equals, and then flipping it upside down gives me dy by dx equals. So here's some for us to do. Let's go through these. I've got x equals y squared. So over here I'm going to every time do my working out. Dx by dy equals 2y. So I reckon dy by dx is 1 over 2y. And that's all really we're doing. Here again I shall write dx by dy equals, well, it's 3y squared. The 7, of course, when I differentiate, 7 disappears, so therefore this implies that, what was that? That was dx by dy. Best to write it properly. And therefore dy by dx is 1 over 3y squared. I hope you're looking at this thinking this is quite straightforward. Here dx by dy on number 3. So tempting to write dx on the bottom, so used to doing it. Now it's 1 over 4 squared, so I suppose that could be written as 4y. No, I've got that wrong. It's 1 over 4y. The quarter is always on the bottom. So it's a quarter of y to the minus 2. I just don't like the way I've written that, so I'm going to get rid of that and do that properly. So this equals a quarter of y to the minus 2. And I've rewritten that specifically because I know a lot of you get those kind of things wrong. So anyway, I bring the power to the front, times by minus 2, that gives me minus 2 quarters, or minus a half I suppose, and I lose a power, so y to minus 3. That might be better written as minus 1 over 2y cubed. So when I turn it upside down to get dy by dx, I reckon I get minus 2y cubed, and it all comes up to the top. The fourth one, well, the very first thing I think I need to do is multiply out these brackets. So I think I get 2y squared minus 3y plus, I reckon, minus y minus 3. So now I know that, I think it's relatively straightforward to do dx by dy equals, and it's 4y minus 1. And therefore, of course, dy by dx is 1 over 4y minus 1. Question 5. Over here, this looks quite straightforward. It's probably one of the easiest ones we've done. 4 comes to the front, that's 8y cubed, and the 5 disappears, so therefore dy by dx is 1 over 8y cubed. 6. Again, this really means y to the half, so just bearing that in mind. Dx by dy equals 20y to the 4 minus, this looks really similar to one we saw before, minus 8. Now, I've got to do half of 8 actually, so half of 8 is 4. And it's y to the minus a half. Oops. Now that's probably better written as 20y to the 4. Well, I was just going to say I was going to change it. I'm not sure I will now. So again, I'm going to erase it. I was going to tidy it up. But I don't think actually it makes a lot of difference. So dy by dx, I'm just going to say, is 1 over a rather horrible 20y to the 4 minus 4y to the minus a half. And the last one, I'm not sure if you can quite see this, that says y and that says y squared. Obviously 1 over both, so I suppose this is better written as y to the minus 1 minus y to the minus 2. So when I find dx by dy, I get minus y to the minus 2 plus 2y to the minus 3, and presumably dy by dx can be written as 1 over all that. Now, I'm going to put this bit first. Now, there's a temptation to say you might be able to tidy this up better, and I wouldn't be surprised if this last one particularly they have tried to, because obviously you've got 1 over a negative power, which is a 1 over. So let's just see what the answers say anyway. Oh, there weren't any answers. I was expecting answers to come up there. But anyway, that's what I've got. That's why I left this big gap over here. Use this derivative of e to the x to prove that the derivative of log x is 1 over x. Okay, that's fair enough. We'll have a go at that. Well, I suppose the obvious thing is it wants me to get this. So temptation is to write y equals log x, because at least then I'm able to write dy by dx equals almost. That's really what I want to do. But the problem is, in order to do this, I need to be able to differentiate log of x, which of course is what it's telling me to do. So rather than doing that directly, I think this is meant to be one where we rewrite this as x equals. And I can do that by moving the log onto the other side, and that would become an e to the y equals x. Now that seems more reasonable, or put a different way, x equals e to the y. Because now I can find dx by dy. And if you differentiate e to the y, you'll get e to the y. So all of a sudden we are now getting to the point where I can write, hang on a bit, dy by dx. I can turn it upside down again. And that's 1 over e to the y, which looks as if I haven't proven what I want. I need to prove it's 1 over x. But don't forget, y equals log x. So I reckon I can probably substitute that back in. Dy by dx is 1 over e, y was log x. Now it makes sense. The e's and the logs cancel, and I've got 1 over x. Aha, we've made it. Another example, the deceleration of a parachute, and this looks very different, is proportional to the square of its velocity. Okay, so proportional, so deceleration, that's a. They would normally, it's proportional to the square. You'd normally write it's proportional to the square of its velocity, but they go a little bit further, because when you get this, you can always then write it as an equation, kv squared, and they go a little bit further. I say by telling me what this k value is. So I've got this value for a, and a, of course, acceleration is dv by dt. So they're telling me that. Okay. And when t equals 0, the velocity is 12. So we've got a piece of information here. When t is 0, the velocity is 12, and we'll probably end up using that in a bit. Find an expression for the velocity in terms of time. Okay. So I suppose what I need is an equation, some kind of function here for v in terms of t. So many t, and I don't know what that is. But the mere fact that it's on this example tells me it's probably a backward one. So why don't I do this? Now I know that dv by dt is that, so I could probably write dt by dv. And bear with me, I'm not sure if this is exactly going to work, but it's obviously going to be 1 over this minus 0.05 v squared. And that is 1 over 0.05 is 20, I think, so it's minus 20 over v squared. So that's dt by dv. Now the reason why I'm doing that is I'm thinking that if I get rid of my v's here, well, when I say that, I think I can integrate this. And if I integrate something that's been differentiated, it basically gets back to where you started. So I think I can get t equals, and it's the integral of dt by dv. Notice you have to do this in terms of v, so you write dv. And that equals the integral. What was dt? It was minus 20. I'm going to write v to the minus 2 dv. And I have to add a power, which is minus 1, and divide by the power. So that becomes 20 v to the minus 1, which another way of writing that is 20 over v. But technically plus a constant. But I am told, now that's what t is equal to. Don't forget that that's what t is equal to. But I am told that t equals 0 when velocity is 12. So t equals 0, and that's equal to 20 over 12 plus c. Now, I don't know what 20 over 12 is. Well, probably work it out. On the calculator, it just comes as 5/3. So just by moving that over there, I could get that c equals minus 5/3. And therefore I have an equation now for t to be 20 over v minus 5/3. Now, I want an expression for the velocity, so presumably I can just rearrange this. T equals, t plus, 5/3 equals 20 over v. I can switch those around. It's v equals 20 over t plus 5/3. Can't imagine that's the answer. Who knows? Is it? I'm not even sure if that's right. Bear with me. No, I've just had a look at the answer. I think I am actually on the right lines. So the bottom part we just tidy up a bit. We put it all over 3 basically. So it's 20 over 3t plus 5 all over 3, because that then gives me the opportunity to bring the 3 up to the front, and it equals 60 over 3t plus 5. And I've had a look. I think that's the answer, according to the textbook anyway. So there it is, v 60 over 3t plus 5. But I didn't really know what I was doing there, but I was willing to have a play. And I suppose I was helped by the fact that I knew this was about inverse differentiation. So that's why I did this first step. I found dt by dv and used this by integration to find what t was. And once I knew what t was, I basically undid the integration, if you like. Once I knew what t was and found the constant of integration, that gave me an answer for t. But of course they said find v, so I rearranged it and eventually got there. I think that's it. Yes, it is. So that's exercise 10e, and we'll practice those in class. And good luck.